This video is going to look at aromaticity. This won't be covered in 3580 until Wednesday's lecture, or lecture number 5. So keep that in mind. If you'd rather wait to watch this until after you see it in lecture, you should wait until after Wednesday. A special kind of conjugation in a ring is known as aromaticity. The most common example of this is benzene, which we've seen before as a 6-membered ring with alternating single and double carbon-carbon bonds. What we now understand with conjugation is that these double bonds are not locked in these specific positions. Resonance allows them to move throughout the double bond, and what we actually see is a resonance hybrid where all of these 6 carbons are the same type, and it's a bond that's in between a single bond and a double bond. These types of conjugation have unique reactivity, and it will be the bulk of what we do in chapter 16. So for example, we can see that those double bonds inside our benzene ring are part of this special unique conjugated system, while the double bond on the outside follows similar reactivity to what we saw in our earlier alkene chemistry. So the goal of this video is to talk about aromaticity, which we're going to call a special cyclic conjugated molecule that meets certain criteria. And let's talk about that a little bit more. These criteria are known as Huckel's 4n+2 rules. And so the rules are that they must contain one or more rings with a cyclic arrangement of p orbitals. Every atom must have a p orbital. The rings need to be planar. This one's a little trickier to see visually. Just do your best to decide based on how the picture is drawn for you. And then the most important one is that it must contain 4n+2 pi electrons, where n is any number 0, 1, 2, so on. In order to count pi electrons, we're going to be counting our double bond as 2 electrons, or you can count each atom as having 1 pi electron. If you have lone pairs on atoms that you can use via resonance to make a double bond, those will count towards our ring. The only exception here is unless the atom already is participating in a double bond. Look at it this way: how many possible p orbitals can it have if you think about the atom's hybridization? And then the last part is, it is possible for an atom to have an empty p orbital that is part of the cyclic system, and if it's empty, that means it's contributing 0 pi electrons. Based on these 4n+2 rules, we have 3 different ways a structure can be characterized. If all of 1 through 4 are true, then you're going to have an aromatic structure. If 1 to 3, or any one of 1, 2, or 3 are not true, you're going to have a structure that's non-aromatic. And if rules 1 through 3 are true, and instead of containing 4n+2 pi electrons, it contains 4n, so examples here would be 0, 4, 8, and so on, you have an anti-aromatic structure. So we can look at benzene and check our rules. We see that we have a cyclic arrangement. Every carbon is sp2 hybridized, meaning it has a p orbital. It's going to be planar. And then what we have here are a single electron from each carbon, or you can say 2 electrons from each double bond. We have 6 total electrons. If n is equal to 1, 4 times 1 plus 2 is 6. And so I wanted to show these pictures here just to sort of give you a better idea, just like what we saw with conjugation, right? Where we saw that the electron density was spread around the entire molecule. That's exactly what's happening with this benzene ring. Here are 2 that are a little bit more complicated. If you want a challenge, pause the video now and try to answer these before I go through them. In this case, the nitrogen already is participating in a double bond, so that lone pair is not going to be able to be used for resonance. As a result, we're going to count the double bond electrons, 1 from each atom or 2 from each double bond. This gives us a total of 10 electrons, meaning this will be aromatic. For the bottom one, that nitrogen is not participating in a double bond. But if we think about a possible resonance structure, we can use that double bond to help participate within the entire system. The resonance structure would look something a little like this, where I'm not breaking any bonds. So I would push the lone pair down to make a double bond, and then those electrons that are in the double bond will be placed onto the carbon. Again, if I look at these, I see that I have 4 double bonds, 2 electrons, and in addition, I have that lone pair of electrons from my negative charge to again give me 10 pi electrons. So this is also aromatic. Here are 6 more for you to practice on. Please pause the video now. For this first one, I see that I have 2 double bonds. That gives me a total of 4 pi electrons. 1 through 3 are also true, but with 4 pi electrons, that makes this one anti-aromatic. For this next one, remember that carbocations are sp2 hybridized, and so this means that this is a cyclic system where every atom has a p orbital. You can also use resonance to help see that. So here, 1 through 3 are true. I have 6 pi electrons, 2 from each double bond. That makes this one aromatic. For this next one, not every atom is sp2 hybridized. Yes, I have the 2 double bonds and the carbocation, but I have a position here that is sp3 hybridized, meaning this is non-aromatic. For this next one, same thing, carbocation, so that position is already sp2 hybridized. However, I have 2 double bonds for a total of 4 pi electrons, which means this one is anti-aromatic. For this next one, both of my nitrogens already are participating in double bonds, so even though those each have lone pairs, they're already sp2 hybridized. That gives me a total of 6 pi electrons, so this is aromatic. For the next one, that oxygen has 2 lone pairs that can be used to make resonance throughout the ring, thereby giving it an sp2 hybridized in certain resonance structures, giving it a p orbital. You can see these resonance structures here, and that's why that's aromatic. So in this case, when I have lone pairs there, I sometimes think drawing the resonance structures out to sort of see, and in this second structure here, you can see that now it's a little obvious that there are 2, 4, 6 electrons, which makes it aromatic. 2 from each double bond, and then 2 from the lone pair. Rather than worry about complex calculations in order to understand why 4n plus 2 is so important for aromaticity, an easier way to do that would be to construct a frost circle. I've sort of summarized what your textbook goes in through, so if you want to refer to that section and page number for some more details, you're welcome to do that. But I'm going to use these guidelines in order to construct a frost circle for benzene. I'm actually not going to draw a circle around my final shape here because it actually deals with more of the energy calculations, but you'll get the idea. So for benzene, we know that there are 6 carbons, 6 sp2 carbons, so 6 continuous p orbitals, so I'm going to start with a hexagon. Notice here my vertex is pointing down, not on its side. Then I'm going to add a molecular orbital at each vertex. So I have 1 here, 2 here at the same level, 2 here at the same level, and then 1 up top. I then am going to draw a horizontal line that bisects the polygon in half. Now every orbital below this is going to be bonding, every orbital above is going to be anti-bonding, and any that are on the line will be non-bonding. So in this case, I don't have any non-bonding orbitals. So I can start to label these. I know that this is going to be my pi 1. These are going to be the same energy level or degenerate, so it doesn't matter which one you label pi 2 and which one's pi 3, they're the same. And then we'll go up. Now we have my pi anti-bonding, pi 4, pi 5 anti-bonding, and pi 6 anti-bonding, since they're above my line. I know that I have 6 pi electrons, so I can go ahead and place them in order. So I'm going to fill in my lowest energy orbital first with an electron going up, then going down. Then I'm going to put electron in my pi 2. I'll need to put an electron up in pi 3 before combining any electrons in the same orbitals. And so then I'll go down, and we can see here all of these are in bonding orbitals. Here is one to practice on. This is the cyclopentadienyl anion. Pause the video now. Here we have 5 carbons that through resonance would all be in conjugation. And so we have a 5-sided polygon. I can go ahead and cut it in half. Now I can go ahead and put a MO at each vertex. I can start from the bottom going up. I have my pi 1. This is still below the line, so it's pi 2, pi 3. Now we're above the line, so we'll be at pi star and pi star. I have 6 total electrons, 2 from each double bond, and an additional 2 from the lone pair on the negative charge. So I can go ahead and put 1 up, 1 down, 1 up, 1 up, 1 down, 1 down. So again, here I can see this as being why this molecule is aromatic.